Um, so yes, welcome from Lafayette. I'm in fact speaking from the Shulgin Laboratory, um, and it's a pleasure to meet you all virtually. I'd like to keep this fairly informal. I've got a group of slides that kind of guide the conversation, but I wanted to talk to the issue of natural products chemistry kind of broadly, and talk a little bit about why one would be interested in doing this kind of work. And I'm going to focus more on kind of the methods and hardware that we use, not so much on chemistry per se, but there'll be some unavoidable slop over into the world of chemicals. With that, I'll get started with slides. So let's see if I can bring this up. So yes, in the title, how did we leave off extraction from the beginning of that? This is going to be extraction, separation, purification, and analysis of psychoactive substances. And what is this? So extraction, by definition, is a set of chemical processes for isolating compounds of interest from some matrix, most often from a plant or plant parts. Uh, this is not something that's out of our normal daily experience. You know, if you made coffee or tea this morning, you were doing an extraction. A lot of ingredients for many of the foods that we have are based on using extracts or purified compounds for flavoring, for coloring. And you know, when you really look at the most broad definition of what's psychoactive, all those substances are psychoactive in a way. They trigger responses in our brains. They increase our appetite or our interest. There's a broad range of possible interests in extracting natural products. As far as drugs are concerned, the number of compounds that we use as medicinal drugs is something like 85% of them on a worldwide basis uh, came from plants originally, or they've been modified from compounds that have originally been sourced from plant materials. Um, the methods and hardware that we use in natural products chemistry are pretty much parallel to the steps and types of processes that are used in a synthetic laboratory for isolation of pure compounds. So there's going to be a lot of slop over between what we call natural products chemistry and synthetic organic chemistry. So let's uh, so and I should point out that you know there's a lot of historical precedents for having kind of intense experience and interest in natural products isolation. Again, as I just said, a lot of pharmaceuticals are based on products from plants or products that have been originated in plants, now may be produced in yeasts or bacteria, but nonetheless have to still be isolated from those matrices. And of course, clandestine psychoactive drugs, as we can appreciate, are often involved with natural products isolations. So every industrial scale process and even sort of a modest preparatory scale process is going to have to be optimized for a particular set of target compounds that we're interested in extracting and the particular characteristics of the matrix that those compounds are in. Uh, Later on, I'll show you comparison between an analytical method and a more bulk extraction method and how the number of steps and the types of processes that you have to go through can differ. The physical chemistry of target compounds and the nature of the host matrix will tailor the approaches that are most appropriate for those isolations. And of course, we should point out that there are legal constraints that may require some forethought as to which of these compounds you want to take on. Uh, uh, there are municipalities and locations in the world where these things are freely legal and other places where they aren't. So we want to be aware of that and take appropriate consideration before we get started. Okay, so the kind of general dogma of an analytical workflow is in this top block. So you select a sample, you have to prepare it properly. You usually do some form of solvent extraction. That can be with a polar solvent, a non-polar solvent, water. Then after removal of that solvent, you've got kind of a sludgy mix. And that material can't necessarily go into an isolation step right away. So usually there's a cleanup operation. Separation can be via a process like selective crystallization or distillation, but often, particularly in analytical work, separation involves doing a chromatography step where you can actually separate individual components and perhaps measure them, perhaps do some further identification work so that you know what the components are. So isolation and identity confirmation can take place once you've got the compounds separated from one another, and the technologies that allow that support quantitation, so you can tell not only what you've got but how much. So starting with analysis is, I feel it's pretty important. First off, it gives you some hands-on contact on how your target compounds behave in your hands, how easy it is to isolate them and or to lose them, and how some of the steps, particularly in cleanup, allow you to visualize their presence, or if you omit it, how they can be sort of obscured from view. So we'll take a look, as I said, at kind of a lengthy analytical process and compare that to a shortcut method that uses selective crystallization to isolate fairly pure compounds. And before one gets started with any of these, plant drying is pretty important. You've got to keep in mind that almost all plant materials are going to be better than 90% water when they first get harvested. That may be to your advantage, but in a lot of cases, have a lot of biological floating around, proteins, glycoproteins, sugars, fats that will greatly impede your progress in that they're still floating around in a water medium of the plant sap. So almost always we not only dry for ease in sample preparation, but also to eliminate the variable uh, of how much water was there in the first place. So virtually all the data that you see on natural products is reported on a dry weight basis. So there are a couple of concepts that I wanted to introduce in some detail uh, because they really impinge on a lot of different levels of the isolation process. So the first one's diffusion. Diffusion is, again, something that we encounter all the time. Dare I say it, the fart that goes off after dinner diffuses through air and is, you all know, that can be a process. Diffusion in liquids is across the board about 10,000 times slower than diffusion in gases. And diffusion takes place in solid media, but at an even slower pace. So when you first start dumping solvent into your powdered plant material, there's diffusion between the remaining particles, as you see on the lower right there, and the solvent medium surrounding it. The particles themselves kind of complicate the diffusion in that they may in fact be quite porous. Solvent has to diffuse in, and once an equilibrium starts to establish, the higher concentration of materials within those particles has to slowly diffuse out into the bulk solvent medium surrounding them. So to speed this up, one of the things that we often will do almost immediately is to finely divide, grind, or mill the plant materials to a very fine consistency. This is not always done, but particularly in an investigative kind of first step, this is usually the first step. The mills you see here are based on, well, the one on the far left, uh, this guy here is actually a flour mill. So it uses like basically grinding between two stones. The Cuisinart next to it is a blade-based machine, and the unit on the right is a micro Wiley mill, which is kind of a laboratory device, but it's very handy for particularly small sample sizes, which you may be encountering when you're doing screening and initial tests. And it's also quite good for very tough materials, bark, roots, and very fibrous materials. So it actually uses a spinning armature of blades and two fixed blades that slice and cut the material that you're trying to grind. And then it falls through a screen into a receiving hopper, and the screen defines the particle size. So you can kind of arbitrarily grind to any degree of fineness. These aren't the only kind of grinders that you'll encounter in a lab situation. There are ball mills that basically have ceramic balls in a rotating vessel that pound your material to a fine consistency. There are cryogenic mills that expose your material to dry ice as the uh, grinding process is taking place so as to preserve volatiles. So, for those of you who might be interested in cannabis, for instance, since the compounds of interest in cannabis are really kind of on the exterior of the plant, a lot of these steps are avoided so as not to lose the very light aromatic terpenes that do contribute to the final aromatic quality of the product and affect the psychoactivity of the final product. So you don't always go through drying and grinding like this, but it's more often than not the case. Okay, the other concept that I wanted to bring up is partitioning. So partitioning is an equilibrium process. If you throw a mixture of compounds into, say, two immiscible liquids, and shake them together, let them stand for a while. The molecules will gradually equilibrate. Part will go into, say, an organic phase, part will stay in an aqueous phase. So those two phases differ in polarity. The compounds that you're interested in may have their own polarity that you want to take advantage of. So this is a process that, in a static sense, like you see in the separatory funnel on the lower right, is very useful, particularly in the cleanup steps of doing an extraction. But also it can be extended to many different variations. So, for instance, you might throw your mixture into a separatory funnel and do a partitioning between uh, methanol and hexane. You wouldn't think that those two would be immiscible, but in fact they are. So you've got a fairly strong organic polar solvent in methanol and a nonpolar solvent in hexane. Separate those two. They're each going to have a group of compounds that kind of match their polarity. And then you can subject them to further different solvent pairs and eventually develop a family of compounds or a family of fractions that differ in their compound fingerprints. So this is the broadest sense. In characterizing compounds from a pharmacological point of view, one of the parameters that you'll encounter is octanol water partition coefficient. So it's a measure of how likely it is that a compound will migrate into fatty substances. And this is important to understand how compounds transport across membranes, where they get stored in the body. And it's one of those pub chem type parameters that is pretty easy to get. And an important one in understanding the distribution of these compounds in animal tissues. But partitioning doesn't necessarily only refer to static situations. So one of the more important processes in kind of all of chemistry, but natural products chemistry in particular, is chromatography. And in chromatography, you have a pair of phases, one of which is stationary, and the other which is mobile. So at the lower left, you can see a cartoon of what would be a particle from a liquid chromatography system, in which case the lower sort of blue sphere is an inert, relatively inert silica powder particle base that's been treated with the pink squiggles, which are hydrocarbon tails, if you will, that extend out into the medium. And your mobile phase here would be often a gradient between first water and then with increasing concentrations of an organic phase, like say methanol or acetonitrile. And as the uh, liquid phase migrates past these particles, compounds in the mixture that are introduced at the head end, as you see kind of in the lower right, will diffuse into that stationary phase, and as clean solvent washes them forward, the ones that are most weakly retained will migrate back out, diffuse into the stationary phase. They see a concentration gradient downstream where they go back into the stationary phase and back out, and gradually compounds will separate from one another on the basis of their differential attraction to that stationary phase. But in each instant of chromatographic separation, you're basically seeing a reestablishment of a partitioning coefficient between now a moving phase and a stationary phase. So chromatography is extremely useful. It allows you to separate complex mixtures into individual components. The types of chromatography that are used depend pretty strongly on what your problem is at hand and particularly the physical characteristics of the molecules that are in your mixture. They are well suited for small samples, even minute samples. I do a routine measurement where a 50 milligram sample is more than adequate. Um, but some chromatographic separations can handle gram amounts of mixtures or even greater. But as I ran into in one book on preparatory high pressure liquid chromatography, if you need to go above a few hundred grams per run, you may have to consider getting a bigger building. So there are always trade-offs between the initial cost of the gear that you need in order to do chromatography, how much solvent is consumed in doing a chromatographic run, how convenient the operation of this gear is, and how easy it is to extract data that can be useful in a quantitative sense. Now, for bulk purifications on like an industrial scale, chromatography is generally a last resort, and this is because the capacity is limited. If you're wanting to produce kilogram quantities, tens, hundreds of kilogram quantities, you may find that it's much more appropriate to use some method like selective crystallization or distillation to purify your compounds instead of relying on chromatography. And it really just gets down to how much solvent can you afford, how much capacity does even a large scale instrument offer you. So I thought I'd go through some of these methods a little bit more in detail. Uh, Probably the most economical and simple way to do chromatography is thin layer. Uh, Thin layer gets its name from the fact that thin plates, usually of glass, sometimes aluminum or even plastic, are coated with very finely divided granular layers of silica or alumina. There are a few other variations. There are even cellulose plates. There are plates that have silica with um, organic coatings, like we saw in the last slide with the particles in a HPLC system. But these are small. Have I got one here? They can be a matter of just a couple of inches in diameter. Um, I've got one here. Let's see. I'll kill sharing to use the camera. There's a thin layer plate. Okay, usually placed in small chamber, a little bit of solvent in the bottom that you can put a lid on so that its atmosphere can equilibrate. Back to the slides.
Paul, there were a couple of questions in the chat that
Oh,
maybe
please. Sure.
one of them from Khalil was about which milling process is preferable for fresh plants.
Oh, I would say, well, you can mill fresh plant, but it's going to be very difficult. Um, Generally, mills will have some screening method to give you a definable particle size coming out of it. And if your plant material going in is wet, it will basically plug that screen. And this is in filtration, at least, it's called blinding. So you basically no longer have a way for your ground material to get out. If you absolutely have to grind fresh material, that would be a case where probably a cryogenic grinder where you throw in dry ice and allow your grinding to take place where everything is kept solid because of the cold. Um, it's a more specialized situation. If you have to do fresh material, that would probably be the best way to do it.
Thank you.
And there was one more question from John asking about roots, and I think that was in like how about roots, which was in reference to you talking about sample plant materials.
Yeah, roots are certainly completely viable. There's maybe an extra cleaning step to remove clinging soil onto them, but they could be kind of chopped up roughly, dried, and then they would go into the hopper of any of these grinders. So roots
My
are
question
fine.
was actually the water content.
I would imagine water content might be a little lower, but I still would be surprised if it was much lower than like 85%. So water removal is always an issue. And again, you almost always have to do that just to be able to get the particle size down to where it's useful going into an extraction. Okay, so as I said, you put small spots of your mixture at the bottom of the plate, dunk it into solvent to where the solvent just hits the bottom below the spots, and then as the solvent wicks up through the silica media, you gradually see the spots differ in migration rate, and you'll start to see separation of individual components. Now the migration rate relative to the like where the front of the solvent is characteristic of compounds. So it's used as a diagnostic. You can identify the compounds in your mixture by comparing with standards. So pretty common technique would be to run a spot of standard next to it, run a sample, a series of samples, and then another spot of your standard at the other end, so that you can kind of bracket and get an accurate estimate of the center of each of those spots. And then you relate that to the distance that the solvent front has traveled, and you get a relative migration or an RF value. I've done a lot of these. It's pretty convenient to do as far as recording and even attempting the RF calculations and quantitation. You can do that with the camera on a cell phone. It's a little bit tedious, but it's also pretty economical. No expensive hardware, no compressed gases, no the solvent use is minimal, and carefully done. The quantitative data from this is entirely valid for particularly screening applications. An even more advanced method of using thin layer in a preparatory sense is one of these centrifugal thin layer chromatography systems, where basically you've got a circular plate that's covered with the silica media. It's held in a housing that rotates the plate at a high speed. And at the left there, you can see there's a little fitting coming in from the lower left. You're basically pumping in your sample in a liquid solution, and then it's followed by more neat solvent that wicks through the rotating surface, and then your compounds spread out as bands, and they eventually spin off the end of those plates. And you can collect that in test tubes or an automated fraction collector. And it can be a fairly elegant way of doing separations. At the lower right there, you see a subsequent static thin layer chromatogram where I've spotted from fractions going through, what are there, about 20 fractions in this particular case. And you can see that there's some pretty significant differences in what's in each of those fractions. None of them are perfectly clean, but they may be substantially cleaner than what you started with, and will allow you to do further characterization, crystallization, whatever it happens to be, to get the extra information you need to perform identifications. Now, another allied technique is open column chromatography. Again, fairly low capital requirements. You've got like a open top glass cylinder with a valve at the bottom, filled with a packing of generally silica gel or alumina, granular alumina particles. Uh, you fill that with the particles, you drain solvent into it, then you apply your sample at the top, and then continue to add more fresh solvent, and gradually the compounds will spread out as bands. Those that interact more weakly with the sorbent solvent combination will elute earlier. And in this case, you're only seeing the last two slides or last two figures in the cartoon actually showing the compounds emerging from the column. It's a simple concept. It's been commonly used for many decades in organic chemistry labs, natural products labs. The first work with ergot alkaloids that eventually gave rise to the discovery of LSD and related compounds is all done with open column chromatography. However, it is rather tedious, and it requires like moment by moment maintenance in order to make sure that solvent doesn't drain below the top of the column sorbent bed. And it's also not so straightforward to monitor in a continuous way, for instance, by UV absorbance. So it's available, but by and large, it's been superseded, and the rotating thin layer technology has been superseded by what's referred to as flash chromatography. So flash is a relatively low pressure liquid chromatography system. Generally, the columns that are used are pre-packed at the factory, so they have great uniformity in terms of particle distribution. The uh, columns are, in the case of silica, are basically designed to be disposable. Used once or maybe a very few number of times, then they lose their resolving power and they're just discarded or recycled. I didn't really speak too much to the issue of normal phase versus reverse phase, but this is probably a good point to bring that up. If you have bare silica in a thin layer plate or in a column like in the device you see on the right there, uh, the interaction between your solutes and the silica is by way of kind of direct polar interaction between the solid silanol groups on the silica particle surfaces and the compounds that are floating in your mobile phase, your mobile solvent. In the case of normal phase, this is where the solvent would be an organic solvent like hexane, or a gradient between, say, hexane and a stronger solvent with higher polarity like ethyl acetate. And in that case, uh, you are dealing with fairly large amounts of organic solvent to get your separations performed. An alternative route is to use particles that have been coated with an organic layer, like we saw in that cartoon earlier. That can be hydrocarbons with chain lengths varying from 4 to 18 carbons, or a few carbons in a straight chain with a phenyl group. And in that case, the mobile phase is generally aqueous to start with, with gradients towards more organic content, switching off to an alcohol like ethanol or methanol, or a compound like acetonitrile. In that case, particularly with water alcohol mixtures, it's much more feasible to be able to recapture and reuse those solvents with some purification steps after. So in any case, uh, these are really kind of turnkey systems. They incorporate sample injection, mobile phase pumping and establishment of gradients, collection of fractions, and monitoring the whole process with UV, or in some cases even other methods of detection. But online detection is intrinsic to these, and of course they're computer controlled. Finally, uh, all the systems that we've been looking at thus far for separations are relatively low resolution. In other words, if you've got a complex mixture with compounds that are quite closely related to one another structurally, it's going to be tough with thin layer or with even flash to get a good separation of those compounds that may be very similar to one another. So for analytical work where we're trying to kind of push those limits, we tend to use either gas chromatography, which you see on the lower right, or liquid chromatography, which you see on the left. The uh, choice as to whether GC or LC is used, first off, depends on physical nature of your analytes. Gas chromatography depends on your compounds being happy living in a vapor phase. So the process involves having your compounds in a solvent that you inject into a flowing gas stream into a very fine diameter capillary column, but they pass through an injector that's held at a pretty high temperature. The solvent vaporizes immediately, and your compounds have to be happy making the transition between being in a liquid solution and being in gas phase, because they're swept then into the column where they're separated and then finally detected. Now, a lot of compounds are not happy with that transition. And for those, you really are forced to use liquid chromatography. As an example, well, let me go. I'll go back and come back to that later. Uh, as an example, sugars, amino acids have very much the same molecular weight range as a lot of the compounds that we're interested in as psychoactives, but they have polar groups, hydroxy groups, other like ionizable groups that prevent them from entering into a vapor phase easily. So for those, we turn to uh, liquid chromatography, and it can be very effective in doing quite complex separations. The equipment is a bit more costly, but happily, there's a very active and viable marketplace in used instruments, and so laboratories that are just getting started can get these systems up and running without breaking the bank. Finally, I'd be remiss in not bringing up mass spectrometry. Mass spectrometry is an extremely valuable adjunct to chromatography systems, and the basis of this goes back to discoveries of how particles behaved in vacuum under the influence of electromagnetic fields, uh, really going back to the Manhattan Project and the physics discoveries of the mid 20th century. So mass spectrometers all share the need to take neutral molecules that emerge from, say, a chromatography effluent stream or even from a solid probe. Molecules have to be ionized. That can be via entrance into a region where there's, say, a heated filament at high vacuum, where electrons flow off the filament. You see that in the uh, left-hand lower diagram. Uh, with voltages applied, the charged particles that emerge are drawn into a separation zone. So many mass spectrometers now use a set of 4 rods that are alternatively, they're pairs, 2 are negatively charged, 2 are positively charged, They additionally have radio frequency signals applied to them. And so particles are drawn into into the resulting electromagnetic field and focused on a detector. There's a sweep of voltages that are applied, and that allows at any instant for only particles of a specific mass to charge ratio to hit your detector. So these devices are all basically small particle accelerators. Uh, the ones on the left are what you see in the simplest instruments, single quadrupole instruments, and triple quads, the variation where three quadrupoles are sort of stacked end to end. These are real workhorse instruments for kind of routine um, analytical work. On the right are the machines that are called high resolution mass spectrometers. And these will have either flight tubes, the parabola that you see on the right hand upper diagram is a zone where uh, bunches of ions are pulsed towards a reflective a magnetic field and then back towards the detector. And the distance is very uh, uh, scrupulously measured, and the time that it takes the particles to arrive at the detector can be very, very accurately measured. So a mass spectrum then is basically the time difference between light particles and heavy particles. And these and the orbitraps, which you see at the lower right, which is basically has a small football shaped zone that's an ion cyclotron, uh, which uh, allows you to collect bunches systematically for measurement. These are devices that uh, seem very complex, but they produce uh, spectra that are really quite lovely to contemplate, and that are highly specific as fingerprints for every molecule. So here you see a mass spectrum from a single quadrupole instrument for CBD, which we all know and love, and shows you on the far right the molecular ion at 314 and the main fragments that are formed in the ionization, the ion source of the instrument. So each compound has a specific enough mass spectrum that, particularly from the single quadrupole instruments, there are now available libraries that you can store on the computer that drives these machines, and compare your unknown against a library of maybe over 200,000 different molecules. So it's a very, very powerful combination. The analysis for even a fairly complex mixture can take as little as 5 to 10 minutes or longer if need be. But the analysis is, almost instantaneous. And it's very, very powerful technology for compound identification. So getting back to kind of the nature of uh, the compounds themselves and what we have to keep in mind in terms of um, how to approach a separation and an isolation. Compound polarity is extremely important. Uh, you see here three compounds that are all relatively close together in terms of molecular weight, but they vary quite wildly in terms of their polarity properties. At the far left is delta 9 tetrahydrocannabinol. Uh, Relatively nonpolar. It has just a single OH group. It's volatile, or in analytical chemist terms, it's kind of semi-volatile. A volatile uh, compound without the semi in front would be something like a volatile solvent, dichloromethane, ethyl acetate. Those are just volatile compounds. Uh, Glucose in the center there, it has even a lower molecular weight, but it is non-volatile. It's highly polar. Uh, in general, if organic molecules have more than two hydroxy groups, the likelihood of their being volatile starts to diminish pretty rapidly, and they definitely are highly polar in terms of being soluble in water and less soluble in organic solvents. And on the right, we've got a situation where mescaline is interconvertible and pretty readily interconvertible. On the left, you see the what we would call the free base form, and this would be the form that predominates if the medium in which the molecule is exposed is basic. So on the right, you see the salt form or ionized form. So if you take the same molecule into an acidic environment, the nitrogen accepts a proton and develops a positive charge. And there's usually an anion. In this case, we're showing chloride ion that becomes associated with it. And this is basically a salt form, which is water soluble. So depending on the pH that this molecule is exposed to, it can readily be in one phase or another without really any covalent bonds being formed. So down below, you can kind of see a cartoon showing that in the red line, going from virtually 100% of the molecule in that form at a low acidic pH, and then as you get more and more basic, it goes through a region where there's rapid change in how much of the material is in that charged form until out at pH 14, very little is present as a charged molecule. But correspondingly, the blue line shows that the free base form will dominate at those higher pHs. So we can definitely take advantage of this, both in an analytical cleanup step or in isolation of pure products in a bulk sense, which we'll see in a minute. Any questions on any of this? We're good? I put you all to sleep. Excellent. We like a sleepy audience. Okay, so let's look a little bit more closely at mescaline. Uh, Mescaline is 3,4,5-trimethoxyphenethylamine. It was the first psychedelic molecule isolated in pure form by Arthur Hefter in 1897. He basically did highly selective crystallizations from peyote extracts and isolated a group of individual compounds, which he then sampled by self-administration until he discovered that mescaline held virtually all of the psychoactivity from that plant. It took another almost 30 years for its structure to be proven by Ernest Spath in Germany in 1919. Now, it's important kind of in our family here because Sasha Shulgin's first exposure to the psychedelic state was prompted by exposure to mescaline. And it turns out that even though they weren't together at the time, his wife experienced mescaline at about the same time via consumption of peyote. And they both found to be a delightful and profound experience. So it triggered a lifelong interest in exploring psychoactive compounds from plants, but psychedelics in particular. The most well-known plant source for mescaline is unfortunately a threatened plant. And this would be Lophophora williamsii or peyote. It's illegal to possess for people who are not members of the Native American Church in this country, but there are several other South American cacti in the genus Trichocereus that also produce the same compound and have been used in uh, the hands of curanderas and native medicine for probably thousands of years. Now, today, there are numerous municipalities in the U.S. that have decriminalized the use of trichocereus-based plant medicines, and this is a relatively recent development that's keeping our interest peaked. So to compare different varieties, we've developed a quantitative analysis approach for mescaline in these cactus materials using GCMS for identification and quantitation. So I want to go through this from both the standpoint of how one runs an analysis and also how one can collect this material for more bulk extraction. So in this case, we do dissect and dry the materials. It turns out that anyone's cut a cactus in half will immediately notice that there's a green band that's shallow underneath the outside cuticle that is green. There's chlorophyll present there. In almost all cases, the green material is where the mescaline lies. There have been some recent reports out of Australia that there are some cactus where the non-chlorophyll containing material can in fact contain mescaline, but the rule of thumb is that the green material is where the mescaline is. So generally, we'll dissect that away from the fibrous center core, dry it out in like a fruit dryer or a freeze dryer, and then to kind of maintain the quality of the material, vacuum sealing and then tossing those sealed bags in the freezer is a very viable way of storing these until they can be processed further. So this is the method that we've developed recently. We take a finely ground sample and take a 50 milligram subsample from that. We weigh it into a small culture tube, add 5 mils of methanol, and spike with a half a mil of an internal standard. Right now we're using methoxamine, which is a closely related material to mescaline. Actually, it has the same molecular weight, but slightly different arrangement of the atoms in the molecule. Anyway, I can talk about that maybe in Q&A. But that sample then is vortex to mix thoroughly and wet all of the material for 30 seconds. You put it in an ultrasonic bath for a half an hour at 40 degrees. This is a step where you're basically imparting energy into the extraction mix. It can be just stirring. It can be stirring with additional heat. There are devices that are percolators that basically allow you to pass solvent through a bed of your sample, almost like a chromatography column. But in any event, there's some means of increasing agitation so that diffusion of materials from the interior of each particle matrix can come out into the bulk solvent. So then following ultrasonics, we centrifuge for half an hour, which gives us a nice clear, bright green extract liquid. We decant and evaporate that to near dryness using a rotary evaporator. And then we rinse that remaining residue into a small funnel with 10th normal hydrochloric acid. So as you remember from the last slide, all or virtually all of the mescaline in that case will be proteinized and water soluble. So we can take that one step to the right and extract it, I would say wash it 3 times with an organic solvent, which will remove fats, waxes, any plant components that are not quite water soluble. By extracting with, I use dichloromethane for convenience, but it could be ethyl acetate, hexane. Then we add some clean solvent, but then make the aqueous phase quite basic by adding a few drops of 25% sodium hydroxide. So in this case, we've now driven the pH in the exact opposite direction. So we've deproteinized the mescaline. It's now in that free base form and much happier to be in the organic phase. And we can extract now with a very small amount. I usually do it twice, first with 1 mil, and then after that's removed with another half mil of dichloromethane. Those are combined and put into a small vial for GCMS analysis. So the final analysis is pretty clean. First off, we, of course, start with pure mescaline to establish a standard curve, which you see on the left. And I mentioned that we use internal standards. The internal standard to target ratio is what is on the x-axis there. So it turns out one of the weaknesses, if you will, of mass spectrometry is the absolute sensitivity, mole per signal out, wanders even during the day. So in order to accommodate that variable absolute response, we incorporate some standard at a constant amount into all of our reference samples for a standard curve preparation, and also in all of our analytical samples where the target concentration is unknown. And then the relationship of the amount of material to the area ratio now, the ratio of the target peak, which you see indicated with the arrow, to the internal standard peak, which is the peak there just short of 10 minutes. And the internal standard is picked so that it has basically the same properties as your target. And so it accounts for the variation in the sensitivity of the instrument output, and gives you a way of stably estimating and accurately estimating the absolute quantity of the material that you're interested in. Now, so on the right is a typical mass chromatogram. This is the total ion chromatogram. So this basically is a sum of all the ions that are produced at the ion source. The inset shows, in fact, at any given point along that total ion chromatogram, there's an associated mass spectrum. Okay, so where the arrow is pointing down, uh, that's where we're seeing the spectrum from that inset. And that, in fact, has two parts. The lines that are pointing up are the experimental spectrum from this chromatogram. The lines pointing down are from a library reference spectrum that's stored in that 200 plus thousand compound library of spectra that we search against. So as you can see here, it's almost a pretty complete mirror image. And that gives us great confidence that the compound that we're seeing, in fact, is mescaline. Thank you very much. So anyway, it's a very powerful technique. These are generally referred to as hyphenated techniques in terms of there being first a separation stage, and then an ionization and mass spectrum separation stage that give you both estimates of quantity and kind of a qualitative uh, piece of information from every point in the chromatograph. So it's a very powerful technique. So by contrast, people who are interested in mescaline have, in years past, been forced to uh, dissect their material, throw it in a pot with water, maybe with a little bit of lemon juice to keep everything in a water-soluble ionized form, uh, make a water extract, boil it down some more, re-extract that first material, boil it down until you have maybe a shot glass full of green goo that you hope has your target compound in it, but that's often very bitter, very difficult to consume, could cause a lot of stomach upset because really who knows what other plant components have been concentrated in that process. So there's been a lot of interest in developing ways to get a purer product that is easier to handle, easier to accurately dose. And so this method really emerged after the method about 10 years ago that was used to isolate DMT from Mimosa hostilis bark. So in this process, dried plant material is ground finely and then wetted with a solution of lime. And this is slaked lime. It can be uh, uh, purified calcium hydroxide from a reagent bottle, or it can be um, lime for marking lines on a soccer field, which would be slaked lime. That's a mixture of calcium and magnesium hydroxides. Anyway, so you make a solution or suspension of that in water, uh, wet your plant material until it's thoroughly wetted through and mixed to sort of a mashed potato consistency. And then you flood that with ethyl acetate, which is a quite benign solvent used in fingernail polish. It is flammable, but relatively easy to obtain. And that's contacted with the plant material for just a few minutes. The ethyl acetate is drained off, filtered if necessary, and then neutralized with citric acid. Citric acid, again, is an easily obtainable food grade product. You can add that directly to neutralize, or it can be added as an ethyl acetate solution. And the clear solution will become cloudy. If you let that sit, the mescaline will actually then crystallize out on the vessel walls and could be collected by filtration. So here are some pictures illustrating the process. At the left and center, these are actually the needle-shaped crystals of mescaline citrate that have formed in this ethyl acetate solution. At the right, they've just been kind of stirred to shake them off the walls. But once they're filtered, they show their native color, which is white to maybe a little bit of off pink or a little off green. And this is very high purity, on the order of 98% of pure mescaline citrate. Um, One has to keep in mind that the counter ion that's formed when you neutralize the mescaline base with an acid contributes to the weight of the salt, and that can be quite dramatic. So the molecular weight of mescaline itself is 211, as you can see on in the table. The hydrochloride is 247.7. So the percentage of mescaline in the salt is only 85%. As you go up through mescaline sulfate to citrate, the percentage of the mescaline base, which is of course the active component, drops quite a bit. So this makes for a weaker product if you want to look at it that way, but it's also well characterized in terms of its purity, so you have a very good handle on exactly how much material you're getting. Also, this material is very, very stable. It could probably last for centuries in this form. Uh, there are a lot of factors that uh, can affect the outcome. Uh, in terms of just the variety of plant material that's going in, we've observed as much as a 40-fold difference in yield from different varieties. So screening for high yielding varieties is very valuable, can be rewarding. We've also heard anecdotally that curing the harvested cactus logs for as long as a few to several months, uh, held in the dark so that they don't try to grow again, uh, uh, apparently tends to increase mescaline content. So whether this is a stress response or something other than that, the plant material is still alive, so it's trying to survive. And one of the results is apparent increase in mescaline content on a dry weight basis. We've also just found recently that the way that the green plant material is dried has a surprisingly large effect on yield. So using our micro method with the methanol extractions and acid-based cleanup, uh, we've scanned these 5 varieties and have so far observed as much as a 69 to 120% increase in yield based purely on the method of drying the plant material, with freeze-dried material yielding much larger amounts than air-dried or fruit dryer dried material. So it's kind of surprising, but we're pursuing this to understand it a bit better so we can take advantage of it. So finally, I'd like to just kind of summarize. Uh, Extraction of natural products is rewarding from kind of the art that's involved, but it does yield materials that can be more accurately dosed, and that gives us materials also that are more predictable in effect because we really know how much is being delivered. The purified products have a greater shelf life. They're also easier to handle in terms of making different kinds of formulations for administration. Uh, I should point out that owing to structure, some materials are going to be more difficult than others to extract and purify. Psilocybin and lysergamides are examples of compounds that are rather more involved, not impossible, but just more challenging to isolate and purify. Psilocybin, since it has a permanent pair of charges, there's generally a negative charge on the phosphate group and a positive charge on the nitrogen. This is in common with amino acids. They really can't be uh, separated using kind of bulk techniques like acid-base partitioning, and chromatography can be challenging in terms of selecting a medium that'll allow it to take place. Lysergamides have the problem of being very easily attacked by oxygen, so they have to be handled carefully and quickly, and uh, they provide their own specific set of difficulties. Uh, Finally, some kind of analytic system to kind of follow screening through attempts at isolation is highly desirable, if not essential. It certainly will increase your understanding of how your materials are behaving in your hands, and it gives you an avenue to really analyze the product quality, quantity, and yield of your processes. So that's the guts of what I was going to formally present. Uh, Happy to open this to questions, and please follow us at shulginfoundation.org and shulginresearch.net. So I'll open it up to questions.
Beautiful. Thank you so much, Paul. Yeah, I'll call on Trip.
Hi, okay. So I've had the burning question for about a week now, ever since I thought of it. And I knew this would be the perfect time to ask. But my question is, what purity did Sasha prefer his compounds to be before tasting them? So if he spent the time necessary to get to like 99.99% pure or better, which is what the FDA would require for it to be used in a study, then he would have limited the amount of compounds he could have made. So I would assume as long as he had removed any potential impurities that might be toxic, he was happy to try them or taste them.
Well, do recall that he left us quite a collection of reference samples, and we have been going through those using GCMS primarily, but also I'm about 150 compounds into the LCMS analysis of those references, and their purity is pretty darn high. Also recall that Sasha came from an era of hot rod chemists who used basically classical techniques like melting points of pick rates, and determining the spread of temperatures at which compounds melted as measures of purity. So he would very often go take a compound between different states, like distillation, crystallization, crystallization from different solvents to improve purity. And I would say he was happy if he was 99% or more, but doesn't really detail that beyond kind of what would be normal practice, which is get it close to 100% pure from review of his notebooks. I don't know if that answers the question.
Yeah, it does answer it. I was expecting like 96% or at that point would be happy, but I'm surprised he spent that much time with them.
Well, remember that Sasha got his chemistry started in insecticide chemistry, and the experience of finding out the toxic nature of dioxin and Agent Orange, with all that was coming out kind of during the time that he was doing his work. So it's well known that minute amounts of highly toxic materials can create real problems. So purity, I think he probably would not have been happy consuming new unknown compounds that were only 96% pure. But that's a hand waving argument. So anything else?
Thank you. Yeah, thank you, Trip. I'm gonna pass it to Jack, and then I'm gonna take some questions from the chat. And I just also want to encourage people, we might not get to all the questions in the chat, so if there are any that you think are particularly useful, like I see people putting some thumbs up on one, so if you could do that as well. But I'll pass it to Jack, and then I'll take one from the chat.
Yeah, and in fact, if there are questions that we can't get to, in real time, let's Jasmine, if you could kind of collect those and collect who sent them in, we'll try to respond in email.
Okay, perfect. I'll keep a log of the chat.
Great.
Thank you.
Yeah, just wanted to say thank you for the talk. I really enjoyed it. I had a question, so it relates to working with cactus material and mescaline. So I was reading something from some amateur researchers, and they were discussing an attempt to steam distill mescaline from cactus material, and they were running into issues. Now, I was wondering if you knew what those issues might be. Were they perhaps making the carbonate with carbon dioxide in the air inadvertently? But they were unsuccessful. I wondered if you knew of any reason why that would not work, or if you tried it yourself before.
I have not. I'm not a huge fan of steam distillation just because of the extra gear that it takes to try to run it. Uh, I wouldn't think it would be a great choice, although I mean I know that amphetamine laboratories sometimes will use steam distillation, partially because the regular distillation is a little challenging because the material is so light that it tends to get sucked right through your apparatus into your vacuum system.
Mm.
Um, but no, I wouldn't think it's a great choice. That mescaline does have water solubility, so it would tend to, I think, want to stay in the water phase. Uh, Knowing how long it takes to get out of a gas chromatograph, the amount of energy that you've got to put into it to get it happily into vapor phase is not insubstantial. So I think the physics of it is just not suitable. It can be for a lot of other molecules, but maybe not for mescaline.
Okay, great. Thank you.
You bet.
Thank you. Okay, I'm going to take one from the chat from Emmanuel. They say, "Hi Paul, would like to hear you talk about a good way to extract psilocybin mushroom, only working with the solvents ethanol, distilled vinegar, and only if necessary ethyl acetate. How can we preserve the shelf life of these psilocybe extract tinctures?" Oh, tincture in brackets.
Well, it's a challenging one. I've not worked with psilocybin extracts for quite a while. I I have heard that you can essentially attempt a different by manipulation with alcohols and temperature. Basically taking dried material, keeping it freezing it, keeping it frozen, freezing ethanol, I believe, and I don't recall offhand the concentration, whether it was 70% ethanol or something higher. But anyway, tossing the mushroom material into cold alcohol, keeping it in the freezer, allowing it to settle, decant, keeping it frozen. I think then there's a step where you bring it up to refrigerator temperatures and then freeze it again, and urea precipitates out. But this is basically a repeated partial recrystallization type of strategy. Ethyl acetate would probably be useful to remove fats if they're present. I don't know how it deals with urea, and apparently a lot of fungi do have a lot of free urea present. So it's psilocybin is challenging. I've tried it a couple of times and kind of walked away from it, but that's not to say that it's impossible. And there is at least one outfit in Vancouver, I think, that claims that they've got a method for creating a shelf-stable liquid extract. But stay tuned for reports from the field.
Thank you, Paul. Okay, so I'll hand it over to Tom to ask his question.
Hi, Tom.
Oh, cool. Firstly, thank you for the talk. Really enjoyed that. I have a question in relation to liquid extractions when it comes to things like emulsions, issues with the phases not quite separating properly. Often, I've seen issues when it comes to using tap water, and not distilled water and tap water being repeatedly boiled down over time and salts in the tap water causing issues with emulsions and things like that. Do you have any tips for that part of the process when it comes to that, or is it just a point of filtering everything super well and having everything as particulate free as possible?
Well, of course, some of the emulsion formation is probably from things that are already soluble. So filtration would not eliminate that problem. I would never use tap water in extractions, just because you don't really know where it's been. So that said, stubborn emulsions can be a problem. If you're familiar with the material for filtration, Sealite. Sealite is used for a variety of purposes in the chemistry lab. But if you have a solvent pair, where you've got a stubborn emulsion, one way to break that is to like in a Buchner funnel. Stop me if I'm using any terminology you're not familiar with.
No, yep, you're fine.
Yeah, on a paper, make a pad of Sealite, start drawing a vacuum on that, and then throw some Sealite in with your solvent mix, and
Cool.
get it well suspended, and then pour that into the filter under vacuum to filter it, and that will generally break up the emulsions and allow you to have to do a clean separation.
Yeah, I've often ended up using like a large funnel with a wet cotton plug, so that the polar phase sort of drips through that, catches the emulsion, and then sort of tipping the non-polar phase off to contain the emulsion on the wet plug, and it gets messy.
Yes, it is messy. Yeah, try that bit of mixing the diatomaceous earth with the material that you're going to try to filter before pouring it on the Sealite pad.
Okay, thank you.
That's called dynamic filtration, and basically you're building up a thicker pad, but you're also kind of keeping things away from each other so that they form gummy layers that blind the filter and block it off.
Yeah, awesome. Thank you so much.
You bet.
Okay, thank you. So I'll take another one from the chat, encouraging people if they have questions as well to raise their hands. But this one is from JD. They say, you mentioned DMT extraction from Mimosa hostilis. Any comments about that procedure and differences from the procedure from mescaline?
Sure. I've only seen this done a couple of times, but it's very similar. You start with the dried, finely ground Mimosa hostilis material. It's wetted with a suspension of base, lime, and then the preferred solvent is heptane. And you mix them together, even for just a few minutes. But kind of the plant-containing phase sort of stays as a lump, and the heptane floats on top of it. You stir it so that they become intimately mixed. Allow all the solids to settle, and pour off the heptane. And then I've seen that just evaporated in an open pan, or you could more formally use like a rotary evaporator, so you could reduce the volume and reclaim some of the heptane for further use. But basically, the free base DMT will precipitate out of the heptane directly, and it can be converted into a salt if you're wanting to consume it in a water phase. But it's possible to even get to a very white crystalline DMT product by then, say, resuspending in warm heptane, reducing the volume, allowing it to crystallize out. So you basically don't ever form a formal salt as you do with the citric acid mescaline process, which I should say has been dubbed the Cielo method. So if you ever run into descriptions of it in DMT Nexus, or you need to do a Google search, that's a term that you can search on.
Thank you, Paul. And yeah, I see there's some confusion for people around how to raise their hand. So at the bottom of the screen, there's a little heart that says react. If you press that, there should be something that says raised hand.
John Niles
And if you yes, Exactly. John, I'm going to pass it to you.
Hi, Paul. That was really great. Is this recording going to be available to people who attended?
Yes.
Awesome. Second question, well, actually more of a comment, Paul. I just wanted to show you since I have my camera on. This is,
I
shoot,
see
where
the
are we?
hands.
This is from the other week and it worked out great. 3 days and it stuck. So I just wanted to show you.
Very nice.
Oh, that's all.
What do you call it? Does it have a name?
Oh, it does. I don't have it in my memory bank, but yeah, I took a picture of the name. It's a bridge, but yeah.
Yeah, I'm constantly surprised and delighted to have new varieties come across our desk, and we've got a growing variety garden here at the farm. So
Are you going to be there? Are you going to be around the farm tomorrow, Paul?
I will be out here next on Tuesday.
Okay.
And I did, you know, if any of you want to stay in contact, I did put my email up towards the end there, drpaul@shulginresearch.net. And I do try to read my email and answer. So there's that.
Thank you, Paul. I'll take another question from the chat from Zach. Any thoughts on the litmus color changing when exposed to the non-polar solvent when partitioning alkaloids and the sensitivity of the partition of specific compounds?
Okay, I think if I understand that right, you're basically trying to get a read on pH of a non-aqueous solution. Yeah, I think I'm getting a yes there. Yeah. Yeah, you can get a pH reaction. Yeah, although in general, most pH indicators do want to have some water present. So what I tend to do is I use these little pre-made strips. Oh, I've got one here. These are commercially available strips that have a little series of bands. Okay. So I'm going to dip that in my drink. Now I see that there's been a change in color. Okay, well, you hold that up to a little comparison. There we go, on the box, and you can read off what the pH is. Okay, well, that works great if your solution is aqueous. What I tend to do if I've got, say, ethyl acetate or some other organic solvent, is I'll pre-wet the strip with just some distilled water, and then with a glass rod or a pipette, I'll take a little bit of the organic phase and just drool it on the top of that pre-wetted strip, and it will give you a reaction that's as accurate as the strip would be if it was in water. It's not ideal, but even using glass pH electrodes sometimes has to take a little experimentation to get a reliable reading from non-aqueous fluids. So I hope that helps.
Thanks. Now I can unmute myself. I appreciate the answer. Yes, I've been having an issue where I change the pH when I'm trying to neutralize the acid, and the pH on a litmus doesn't match the pH on the color code. So I'm a bit torn determining whether I've got a pH of 6 or a pH of 8, and it doesn't seem that I can make any changes and match the color on the natural or on the original pH code.
Okay, so something in your system is interfering with the normal color chemistry of those strips.
Well, there's ethyl acetate in there, and you've mentioned that already. So it's about 10% soluble in water, and yeah, so I'm having that issue, and then the final alkaloids are a little bit of a different color if I use different pHs for the extraction. If I use like, yeah, well, a very concentrated or a dilute concentrated hydrochloric acid solution, I'll get a much different colored alkaloid extract out of the solution. So I'm wondering
Yeah,
just how important it is to know your pH and if the litmus is that accurate. But thank you for your feedback. I appreciate your feedback.
yeah, it's what you're describing is I've seen as well. What I've noticed is that getting the overall acidity, like is it 10th normal? Is it 1 normal? It can have a kind of surprising effect on partitioning of alkaloids between phases. I can at least remember one situation where I tried, I think, 1 normal HCl, and I was getting very, very poor recovery of the target compound I was after. But using 10th normal, I was able to, you know, easily see the compounds I was after. So this is something that you just have to experiment with, and hopefully there's some accompanying analytical method like a thin layer or some other way of even ultimately just taking it all the way through your process and weighing the product to evaluate which is going to work best. There's no substitute in the chem lab for doing the experiment and using all your senses, whatever sense modalities you've got.
Yeah, thank you. Thank you for your feedback.
You bet.
Great, thank you. I see, Etienne, you had your hand raised a few times.
Hello?
Yes, we hear you.
Yeah.
Hi. Yeah, I don't know. I kind of was apprehensive because it just seems like one of those things that requires experimentation. I have also been having difficulty with the mescaline extraction technique, using the citric acid and the lime. I don't know. I just don't get that the reactions that I'm seeing as reliably as I do other people's, and I feel like I'm pretty consistently trying to follow the instructions as I've been researching them. I'm sure there's some variation where something probably just requires some adjustment. So it's just why I was apprehensive to ask, because it seems like just something I have to figure out over time. But if anybody has tinkered with it enough and just wondered why is there just no precipitation reactions, and then is there a solution, it just seems I've definitely gotten mescaline hydrochloride extracts to work out more reliably, and they take me a few days to actually do, whereas the over-the-counter one that's supposed to be quick is almost like not seamless for me. So it just feels like the molecules are not behaving.
Well, the molecule gods sometimes smile and sometimes they don't. So one question, so after you've wetted your material with the lime water, what happens next? Are you going straight into ethyl acetate? Are you drying the material first?
I remember I was reading that it has to settle for a little bit, but not for too long so it doesn't congeal. And then I just directly transfer it into the French press, and I
Okay.
and then I'll do a solvent pull, and then proceed as directed.
We probably should talk offline, but I have observed that the amount of water that's present has an impact on this whole process.
I thought that too. Yeah.
Yeah, I've dried the material to very hard dry using microwave. I've tried drying it, but sort of halting the drying process using a freeze dryer and using it more or less, kind of wet going into the ethyl acetate. And the hard dry gave me a 0 yield. The partial, incomplete freeze dry gave yield that was more kind of to my anticipation. If you contact the wet plant material with ethyl acetate, there is going to be a fair amount of water present. If you decant or squeeze out the ethyl acetate, you can throw that in the freezer and basically freeze the water and then filter it quickly in over a filter paper. with vacuum filtration. That gets you down to a low amount, but kind of you know, as determined by the freezing, kind of a fixed amount of water that seems to be about the right amount to allow the crystallization to take place. But
The-
you know, it's
the-
your mileage may vary kind of proposition.
The freezing of the solution is the one aspect I haven't really experimented with, but I have ensured to really dehydrate my sections pretty thoroughly. And my next hypothesis and something I want to work with is material that's been cored. So you're just working with the skins. You basically create like a onion ring of cactus, and all the middle part that's just water would be eliminated anyway. So I feel like that's also key, is if you prep just skins and the outer cores rather than including any of the whole ring, you might just make it more efficient.
Yeah, that inner fibrous material I think is pretty generally assumed to not have much alkaloid in it. But there, for instance, there's a quite a lovely paper where a surface probing mass spectrometry was used, where basically they rastered samples in front of a fixed orifice, so that you know, basically a picture could be made of where different ions were located, and they used a slice of San Pedro for that. And in fact, that zone just inside the outer cuticle that's green is where all the 211 signal was located. So they were able to actually visualize the location of mescaline in a cross section.
Yeah, that makes sense.
But we can
Thank
discuss
you.
this at greater length.
Yeah, definitely. Thank you so much for your time. This was a lot of fun. Thank you for doing this.
Yeah, so I see we're at time. I don't know if there's time for any more questions, but as Paul said, we'll take you know, a log of the chat, and Paul can respond to each individual question, and with the recording, I can send you along the responses. So I think, yeah, maybe we can wrap up there. I just want to say thank you, Paul, so much for joining us, for your wonderful expertise, and it's such a treat to have you beaming in from the lab as well.
Well, it's been a
And
pleasure.
also, yeah, for those of you that want to continue supporting Shogun Foundation, I've left a link to donate in the chat to learn more about us and to stay yeah, in touch about future events. There's a link to join our mailing list, so you can be informed of online and in-person events at the farm. Yes, I will send an email out with the recording through Eventbrite, as well as the questions answered. But that might take a couple of days. I think that's everything. Well, thank you, everyone. Thank you, Paul.
Well, thank you all for coming.
Thank you.
Thank you.
Very
Thank you
well.
so much.
Thank
Okay.
you. Bye.